We start now with the first talk. First talk will be given by Professor Eli Yablonovitch from Berkeley University, California, University of Berkeley. יש משהו לנגב פה? Okay. Eli was the inventor of the photonic crystal, but not only this, he also made additional very nice contribution to the photonic area. One of them is what is called the Yablonovitch limit of solar cells. I'm sure that we'll hear about this a little bit. Also, he was the one that predicted that strained quantum wells or strained layer can improve the efficiency of semiconductor lasers. And when I met him first, he was at Bell Core. He was very busy in developing a technology that now is, I believe, is used in the solar cells, which is called the liftoff, epitaxial liftoff. And I'm sure that he's going to talk about today. And Eli.
Okay, well, thank you very much. Okay, it's great to see everybody here, and it'll be my pleasure to talk about solar cells. It is one of my favorite subjects, and it has many aspects to it that are not completely science. Some of it involves society, economics, and many other things. Here, let me turn the pen on. All right. So everybody has seen solar panels, particularly if you travel in parts of Europe. You see vast areas are covered with solar panels. It's quite an amazing transformation. When I started work on this was over 30 years ago, and it was a very, very tiny industry. And you can imagine how it has grown if you extrapolate the exponential backwards, back not to 2000, all the way back to 1980. You can imagine how small it was back then. It was truly a tiny industry. But it has become a very big industry. The shipments in 2011 were close to 25 gigawatts installed that year. And then this past year, probably it was closer to 30 gigawatts. So it's a very, very large industry, and somewhat surprising. I'll be candid with you, I'm not completely happy about the great expansion of the industry, because a lot of it was based not on real improvements of technology, but rather was based on subsidies, which are, don't necessarily always favor the best technology. But to give you an idea of what a big political commitment can do, here's the electricity generation in Germany. And we chose a special day last May. And let's say we chose Saturday, May 26th. And if you look at the solar and the wind, it represented half of Germany's electricity. And Germany is a very big country. And on that particular day, half the electricity was coming effectively from solar and a little bit of wind. And you could wonder, how could this be? Well, you have to choose the day very carefully. Obviously, on a Saturday, they don't necessarily have so many people working. The factories are shut down. They don't use so much electricity. So that's a good day to pick, because then the solar will look very big. And then the second thing to remember is, well, it's a sunny May is sunny. Of course, June is even more sunny. But the solar cell is a small thermodynamic engine. And like all thermodynamic engines, it's more efficient when it's a little bit cooler. So the peak production by solar panels is not in June, it's actually in May. And nonetheless, it represents a tremendous achievement. Approximately half of Germany's electricity coming from solar energy. But that's also a very big political commitment. It has cost them a huge amount of money. Some estimates I've heard about $100 billion invested to make that possible. So it's an example. This is not a small technology anymore. It's not a small industry. It's quite remarkable. And of course, there's a story. Why did this happen in Germany? And I'm told it has something to do with the Green Party. Okay, but I'll leave it at that. But the technology has actually improved tremendously. This graph starts in 1985. I apologize for the small font, but it was hard to squeeze everything in. And if you look at the cost of production, well, it started really in the 1980 was maybe $10 a watt, and then it kept going down in price and down in price and so forth. And you saw very significant changes up until about 2005. And then the German subsidies kicked in, and they were buying so much silicon. They had a shortage of silicon. So for a very brief time, there was a shortage of silicon, and the price went up. But that was only temporary. Then they produced enough capacity, and then now the price is continuing to drop. But I would say the last drop we're seeing in the past few years are due to not technology improvements, but rather due to production subsidies. So Germany had big installation subsidies. Now China has very big production subsidies. They built many factories, too many, and they're having a price war, and the price has become very low. Now, often in business school, they teach about the learning curve. That is to say, every time you produce by a factor of 2 more of any product, you become more efficient. The society, engineers, everyone becomes more efficient, and the price tends to drop about, people estimate, maybe 20% drop in price for every factor of 2 increase in volume of production. So most of it, though, is very much due to science. Tangible scientific and engineering improvements have been made. And this is a simplified graph. This goes from a price of $10 a watt, let's say about 30 years ago, to up to the present. Well, the present is actually somewhere less than $1 a watt. So it's about a factor of 10 decrease in price. And that's due to real technology. That is due to actual scientific changes, cleverness, ingenuity, and so forth. However, we shouldn't underestimate it, because it's not just a factor 10. During that time, the dollar became less valuable. And if you take into account inflation, that means a factor of 30 of real reduction in the cost of solar panels. And one can identify the specific scientific and technical breakthroughs along that 30-year period that made it possible to reduce the price. So it's very, very impressive in that way, especially if you go into the details of how they did it. A factor of 30 over 30 years is about a factor of 3 real price reduction for every decade, for every 10 years. So that's quite interesting. Now, there are some projections. Maybe, well, today we probably have maybe 80 to 100 terawatts installed. And maybe by 2020, there will be as much as gigawatts cumulative installed. Let me get rid of the T. And that gets rid of the T here. And then we have eventually in 2020 about a terawatt installed. That's truly a huge amount. It is thought by some people that maybe in 2016 there will be subsidies will no longer be needed, but we're not certain. So a lot of scientific improvement. Now, the scientific improvement, though, has a little bit of controversy associated with it. People question what is the best approach. There are many approaches toward making solar cells and making solar panels. And this is not something that we do as scientists in isolation. This has to be part of society. People argue, is it most important to have high efficiency? Or maybe the cost of the panel is more important, the efficiency matters less. There have been many arguments. I tend to agree with Professor Barnett here from the University of Delaware. This is one of his graphs. And this is a common equation for the cost of electricity. And not surprisingly, the efficiency ends up in the denominator. So if you want to have a low cost, you have to have a high efficiency. But it's a very, very controversial point. Not everybody agrees with this. And in particular, the stock market does not agree with the equation I just showed you. This is the stock price of First Solar. This is a public company that makes cadmium telluride solar cells around 11% efficiency. And the market, well, let's look at the market here. This company is worth over $2.5 billion. So the stock market respects that company. Now here's a different company, which is a very efficient company, 23% efficiency. And it's very clever, a lot of beautiful science. I know the founder, he's a very smart guy, but the stock market does not respect this company so highly. It's less than $1 billion in value. And so they say, don't argue with Wall Street. Well, I'm arguing with Wall Street. I think maybe this is the wrong priority. Maybe efficiency should be the highest priority, but it's controversial. And who am I to dispute the wisdom of the entire stock market? So I will tend to emphasize efficiency because I do believe that equation where the efficiency appears in the denominator. If you have double the efficiency, that means you need half as much glass, half as much semiconductor, half as much processing, half as much land, and half as much construction. It's very hard for me to believe that that won't end up being less costly in the long run. So that's my sociological interlude, is just to show that while I emphasize efficiency, it will not be the only story. Now, we come then to some scientific questions. And I will take a little bit of a contrarian viewpoint in solar. And so I'll have a bunch of questions I'd like to answer. First, you see, I'm going to argue that the p-n junction really should be optional. It's not absolutely necessary. People think the p-n junction is the most important thing in a solar cell. Now, I don't agree. I think it's used, but it's optional. There are certain types of solar cells where the p-n junction is not used at all. And then I will try to answer what determines the voltage of a solar cell. And the reason is that almost nobody talks about this. Everybody talks about the current in the solar cell. And the current you need to have, it's like the knowledge of an accountant. An accountant has to keep track of the money going in, the money going out. And if you keep track of that, you'll get the photons going in, the current going out. You'll know the current. The voltage is much more subtle. The voltage comes from thermodynamics and statistical mechanics. And so I'd like to show that it is not that hard to explain the voltage. Then I'll talk about the system mechanical approach to optics. It turns out the optics of the solar cell, I think, is now being recognized as being of equal or even greater importance than the electronics of the solar cell. And then people always ask me, are photonic crystals of any help towards solar cells? And my answer has changed a little bit over time. And then I will close with more of a business conclusions. What are the top competing technology? What is the status of the industry, et cetera? So first, I will try to describe what is a solar cell. And in this respect, I think of the solar cell as a type of container that contains electrons. And think of this container, well, you think of it as being made of silicon. And you have a silicon container. The photons are coming in, and they produce electrons and holes, and they are essentially a container for electrons and holes. Now, the biggest problem in a container is how to keep the electrons and holes on the inside, and because if they run to the surfaces, they might recombine. So invariably, in optoelectronics, the outside of the semiconductor material is a material with a wider band gap that keeps in the electrons and holes. In the case of silicon, the wider band gap is simply silicon dioxide. And indeed, this is used in most of the world's solar panels today. So you are trying to build up a very high density gas of electrons and holes. Why do you want a high density? The density relates to free energy. So in solar cells, you have two free energies, one for the electrons and one for the holes. These are separate free energies, and they are separated by a certain voltage. Now, if you have a contact, an electrical contact, that only sees holes, then you will see this voltage. And if it only sees electrons, then you'll see the other voltage. And so you have two voltages, two Fermi gases at two different chemical potentials available, and so you have the possibility of extracting electricity at a certain voltage. Now, notice that in this entire discussion, I have not invoked the p-n junction, because in this type of solar cell, there is no p-n junction. It's not completely essential, but there's a little bit of a trick. You need to make a contact that only sees electrons and another one that only sees holes. These are actually the type of contacts we normally make. And so I would say you don't necessarily require a p-n junction. So you look at this and say, but there's a trick. How do you make the selective contact? So let me show you a little bit how to make a selective contact. First, I also have to show you why we use the silicon dioxide. We really don't want the electrons and holes to recombine at dangling bonds. The surface has many dangling bonds. Okay, and so you have to coat the surface. This is a standard thing in electronics. You coat the surface with a wider band gap material so there are no dangling bonds. And then the wider band gap keeps the electrons and holes in. So how to make a selective contact? Well, here is an example. Suppose you have a heterojunction like this, and the electrons go freely to the metal, and the holes, they don't make it. They get turned back. Likewise, the electrons get turned back here, and here the holes go freely to the electrical contact. So it's possible to imagine. They're actually, this is something that metallurgists study their whole careers, is how to make a good selective contact like this. But it's known how to do that. And this is just one way of doing it, one type of selective contact. So these things exist. So what is my preferred model for solar cells? Is, well, you may think it's simplistic, but I regard it as the leaky bucket model. Imagine that you have a bucket and it is containing, capturing raindrops. And the raindrops are like photons. So the raindrops are falling into the bucket, and they are building up a certain amount of pressure in the bucket. And they're also able to flow. So you open the valve, and the water flows. It comes out with some pressure, so it turns a water wheel, and the water wheel goes around. And there are two ingredients to the power of the water wheel. One is you need a flow of water, but you cannot ignore the pressure. The water should have a certain amount of pressure. Of course, the flow is the current, and the pressure is equivalent to the voltage. And so this captures a lot of the science of the solar cells. For example, what could go wrong in a solar cell? Well, we could have a leaky bottom in the bucket, and that would prevent the pressure from building up. Or we can have leaky sidewalls, essentially recombination at the surfaces. And so the sidewall leakage is like surface recombination. The bottom leakage is like bulk recombination. And so you could visualize that picture. And I'll get into this in one more slide. I'm going to go very quickly to the three important things to know about a solar cell. You certainly want to know about the current. You want to know about the voltage, and you want to know if you can get them both at the same time. This is called fill factor. And I'm going to explain these in sequence, and they have all of them have some interesting physics aspect. So let's talk about the fill factor. What does this mean? Well, suppose we have our bucket model, and we have the raindrops coming in, and but we open the valve very, very wide open. A huge flow of water comes out. And as there's so much water coming out, you build up a very little pressure. And as a result of that, this is a bad strategy, because it means there will be very little pressure, so there'll be very little work done by the water wheel. On the other hand, you could go to the opposite extreme. Keep the faucet closed, so it's almost completely closed. Only a few drops come out. You build up a very high pressure, but the current is very low. And so this is also not very good. You get very low flow, but you have, so very low current, but very high voltage. So in reality, you have to optimize both at the same time. And so you have to find a balance between the pressure and the current. And when you achieve the perfect balance, you get the maximum work done by the water wheel. And it's very much the same with solar cells, you cannot get simultaneously the maximum voltage and the maximum current. Well, if you get the maximum current, you have no voltage. And if you get the maximum voltage, you have no current. So you have to compromise. And the compromise looks something like this, that you get a certain amount of voltage and a certain amount of current, but the size of this rectangle is smaller than the imaginary power. If you had the maximum voltage and the maximum current at the same time, it would be the bigger rectangle. And you cannot achieve that. And so the ratio of the two rectangles is called the fill factor. And so this rectangle is smaller than the big one. And in fact, it's not that much smaller. It's about 80%. In the most ideal conditions, it's 89%. And so this might be regarded as, oh, well, it's kind of unfortunate circuit property, but actually it's very fundamental. And I want you to think in terms of statistical mechanics. Statistical mechanics says it's very unlikely that you'll get all of something and nothing of something else. In statistical mechanics, you're looking for the maximum probability. It's always a balance between two extremes. And that this limitation in power output of the solar cell, this 80% limitation, is really given by statistical mechanics. And that means it's given by fundamentals. It's not something we can change. So it's not just an unfortunate circuit property. Okay, so I've left the concept of fill factor behind. We'll touch on it again a little bit later when we talk about the voltage. Now I want to discuss the current. And I notice we have a very big audience here, but everyone is very quiet. So if you want to interrupt me, please interrupt me, challenge me, question what I'm saying. Does anyone object to anything I said so far? Okay, so you'll have time to object some more as we go along. All right, so now I'd like to talk about the current to accept. Obviously, you want to absorb all the light, and you want to use as little material as possible. Obviously, therefore, a direct band gap is better than indirect band gap. So that's the starting point. I'd like to talk in a little bit more depth about the optics of solar cells, which has now emerged as the most important factor in achieving very high efficiencies. And you'll see that as we go along. Now, the picture of solar cells, it used to be the picture that the light ray would come in, and it would refract, and it would go out. And effectively, you had one chance to absorb the light. It would go through the film, and whatever absorption, that would be it. Okay, now, then it was realized, whoa, that's very bad. And they used to make solar cells this way up until about 15 years ago, that the light just went in and it had one chance to be absorbed. But it was noticed that, wait a minute, if instead of a plain parallel slab, instead of just something that's plain, if you had even one surface wavy, if you break a little bit the symmetry, what happens is that the light ray would come in, it would be scattered at a strange angle, and then would be scattered at another strange angle, and after one or two bounces, the light ray would have no memory of the original angle. And in fact, the light ray could fill the entire phase space, would fill all the internal angles inside the semiconductor. And obviously, the path length of such a light ray is much longer than that path length. And if you try to do a detailed calculation how much the path length would increase, it was given, just in geometrical optics, it was given by the refractive index. And the formula is 4 times refractive index squared. Well, you say, oh, that's just something of order of magnitude unity. But actually, the refractive index in a semiconductor is very high. It's 3.5. Squared is 12 times 4 is 48. Let's round it off to 50. So the path length could be increased not by a small numerical factor, but by 50 times. And so this is a very substantial effect. And in fact, it's very analogous to the understanding in light-emitting diodes. So in solar cells, we went from this, we went to this. We break the plane parallel symmetry, and suddenly we have 50 times greater optical path length. In a light-emitting diode, you have a very analogous problem. In fact, the light-emitting diode is the reciprocal of the solar cell. One takes in light and gives off electricity. The other takes in electricity and gives off light. They are really the same device. So let me show you how they're the same. Suppose we have an LED and it emits a light ray. If it's inside this escape cone, the escape cone is quite narrow, maybe 15 degrees. Well, it escapes, and you get some output from the LED. Unfortunately, that's a very small percentage. If you calculate the solid angle compared to all the possible internal angles, that angle of light escaping is only 2% of all possible angles. 98% of light is totally internally reflected, back and forth reflected, and that light reflects over and over again, back and forth, eventually gets absorbed, wasted, and the old LEDs were only about 2% efficient. The industry, of course, realized this is pretty bad, so it's been corrected now. Now we have much more efficient LEDs, but it's again breaking the symmetry. Instead of having plane parallel, you break the symmetry. Maybe the light ray doesn't escape right away. Eventually, it will hit at some random angle and escape. And so we see then the reciprocity between the solar cell and light emitting diode. They are both trying to make the light rays appear to be very random. And only then do they perform very efficiently. So this is very strange to talk about the light ray. And in fact, I will now give an example at the kindergarten level of the strange optics that can occur. Now, of course, this is not kindergarten. This was graduate school. I took my class in statistical mechanics. The professor explained to me what is ergodic. I almost got a headache thinking about what is ergodic. Okay, and after the class was over, I said, thank God I will never have to use that word again. Okay, however, here it is, where in the kindergarten level, we have to use the word. Okay, and I will try to indicate how it works. Suppose you're a child and someone shows you a sphere that's a shape, and the light ray comes in, it refracts, and it goes back out again. It works a little bit better with the pen. It goes in, and goes across, and goes back out again. The light rays do not explore all the internal angles that are possible. Only a certain angle is achieved, and so you only get one pass. I already described the rectangle. You only get one pass. The parallelogram is just like the rectangle. These are shapes that are very limiting. They don't allow the light ray to explore all the possible angles. Now, this is to be contrasted with the ergodic shapes. And so we have a shape of an ellipse. An ellipse is qualitatively different from a circle or a sphere. The reason is that the light comes in, and it starts bouncing at strange angles, and after a few bounces, it explores all the possible internal angles. In statistical mechanics we would say it explores the full internal phase space. So ergodic shapes, the time average is the same as the phase space average. That's the meaning of ergodic. It means with time, you will eventually explore all angles. The trapezoid, another shape, well, it's an odd shape, but the angles bounce and bounce, and the light ray forgets the original angle and fills all the internal angles. So these are very advantageous in optoelectronics because if you have, for example, if you have an LED, all the internal light eventually escapes. But these shapes, which are commonly used, the rectangle and the parallelogram, these shapes are very disadvantageous. So here, in a simple way, the words ergodic and non-ergodic, but at the level of very elementary shapes. There's a qualitative difference between the different shapes that a child would learn. And what it tells us, we should try to make our optoelectronic devices out of ergodic shapes. So I mentioned the factor 4n squared. Where does it come from? Well, the mode density, if you think in statistical mechanics, there's a refractive index squared in the mode density. Then there's a factor of 2 because the light ray bounces back and forth, and there's a more subtle factor of 2 because the light ray is bouncing at an angle, so you get an increased path length. And after everything is worked out, it's 4n squared. Now, this is a quite significant benefit. Obviously, it means you can make the semiconductor very, very thin, and the semiconductors cost money. So if you use less semiconductor, you can bring down the cost. Another advantage is that you can make the solar cell much thinner. There's less series resistance, and you could end up with this fill factor I talked about. You would be able to get the voltage and the current higher. And finally, this is a little bit more subtle. You have concentrated the sunlight into a thinner layer, 50 times thinner. Whenever you concentrate anything in statistical mechanics, the free energy goes up. A concentrated resource is more valuable. And so you get more voltage by kT log of 4n squared. And so you increase the voltage. This is natural log of 50 is about 4. So you increase the voltage by about 1/10 of a volt. But people sometimes get upset about this as they say, well, how can you rely upon total internal reflection when you have to have an anti-reflection coating? And the English language is very strange. It seems like these two things are opposite. But actually, they're very much the same thing, or they're certainly compatible. The anti-reflection coating only applies to the light rays that are in the escape cone. The light rays that are going to be internally reflected are still internally reflected. So they're both mutually compatible, and a good solar cell has total internal reflection, and it has an anti-reflection coating, both. Now, one of the things, I wrote about this about 30 years ago, and I said, look, in statistical mechanics, you already get you have this 4n squared factor, but if you have just a random surface, a random shape, you already approach the statistical mechanical limit, so there's no point trying to come up with some subtle shape because random roughness already achieves the theoretical limit. Nonetheless, over these past few decades, there has been actually a huge amount of work trying to beat the 4n squared factor. And I would say some people think they have beaten it, but people ask me, maybe if you use a photonic crystal, you can do better than a random rough surface. And there's hope because this theorem depended upon geometric optics, and in wave optics could be a different situation. So let me show you what we've done to try to answer that question. And I'll try to be practical about it. Suppose you have a good direct gap semiconductor like gallium arsenide. 3 microns is more than enough to make a good solar cell. Now, if you use this light trapping factor, that means the film is going to be very thin. It could be 50 times thinner, so this would be only 60 nanometers thick. Obviously, that's much less than a wavelength. And so you can't use a geometrical optics argument. In fact, what you should think about is how you could possibly texture such a thin film in order to trap the most light. So it leads to the following question. What is the optimum surface texture on a thin film that will absorb the most light? And it is obviously not a plain parallel film. It is a film with some texture associated to it. So let's try to solve for that. It's a mathematical question, almost. Well, it is. It's very mathematical. So we approach this, and we approach this with periodic boundary conditions, and we try to solve for what is the optimum shape. And you can imagine that maybe it's a square array like what I've shown, maybe a square photonic crystal like this. And we've used a mathematical approach for inverse solutions. And you need a figure of merit. And the figure of merit is by how much you increase the absorption. And I see my numbers here are a little bit messed up, but this is 10, 20, and 30 times enhancement. So these are big improvements in the enhancement. And there's some subtle technical things. What is the figure of merit? I'll just mention in passing for the people who care. We optimize for the worst performing wavelength in this frequency band. And this is the frequency band that happens to be relevant to gallium arsenide. And so what I will show you is the outcome of this optimization. And let's see, I thought I had a movie here, and maybe I do. Let's just see. Well, my movie has disappeared here. Sorry about that. Let's just go on. And the result of running through these iterations, let's see if I have it here. Yeah, Yeah, this seems like my movie has disappeared. Let's just see if it's still here but is hidden. Yeah, okay, it looks like that particular slide did not make it. All right, let's go back to the talk. The result of this iterative procedure, mathematical procedure, is to come up with some shapes that are actually breaking the plane parallel symmetry. And we end up, if we restrict it to some type of symmetry, we end up starting with random perturbations. We end up with these oval-shaped structures. And in fact, if we allow it to evolve further, we find out that the optimum domain for trapping light in the thin film is up here in the, very high in the photonic band structure. So this turns out to be the optimal region. We call this the spaghetti region of the photonic crystal, where you have very, very many optical modes that are present. And if you completely allow the optimization to carry out without constraints, you invariably end up with a very asymmetrical solution. And there are many very asymmetrical solutions. Here you see about over 30 times enhancement factor over the entire band. But surprisingly, you end up with very much of a broken symmetry in the course of doing that optimization. So it's very surprising what you end up with. And this was a little bit of an aside, but just to indicate that it seems to be desirable to have broken symmetry even in the wave optics regime. Okay, so I've discussed a little bit about the current. The main point about the current is you can get a lot more current than you expect. You can make it much thinner and so forth, and there are a lot of benefits associated with it. Now I'd like to talk about the voltage. The voltage, we have this container for the electrons and holes, and I'm going to talk about what is the highest voltage we can achieve. And well, you could argue that maybe the open circuit voltage is not as important. We should be looking at the operating voltage, which is slightly lower. But this has to do with the fill factor when we make the compromise. And if we compromise a little bit the voltage in order to give the electrons and holes a reason to leave the semiconductor, go into the wires, to go into these wires, we just give up a few kT of voltage, and we end up with a very high operating voltage. So I will, for this reason, I will emphasize the open circuit voltage as the quantity that we're trying to optimize. Now, how to determine the voltage? It's a little bit subtle and hard to explain. So, but if you trust me, and if you trust the Boltzmann factor, I can derive the open circuit voltage for you. And so let me invoke the Boltzmann factor. Let me get the pen activated again. So I have here the Boltzmann factor. And the Boltzmann factor, everybody knows what the Boltzmann factor is. It's the ratio of probability. So I want it to be the excited state population in the light and divided by the excited state population in the dark. Even in a very dark solar cell, in blackness, there are still a few thermally excited carriers. So this population ratio is a type of Boltzmann factor. What if I invert the Boltzmann factor and I calculate the free energy? So I'm going to say the free energy is the voltage. So then I get the natural log of this population ratio. And kT times a natural log. This is a very typical statistical mechanical formula for voltage. So if you believe the Boltzmann factor, you arrive at this conclusion, and you get this rather interesting result. Shockley went one step further. He said, well, wait a minute, how do I know what is the excited state population? That determines the light emission. If you have an excited state, it can emit light. So I can rewrite that as the luminescent emission when it's excited versus the luminescent emission in the darkness. Even in darkness, there's a small amount of excited electrons, and therefore there's a small amount of spontaneous emission. So he converted the population ratio into a spontaneous emission ratio. And then Shockley had an inspiration. He said, look, in the most ideal solar cell possible, the incoming sunlight has no place to go. At open circuited, the current cannot go into the wires. Where does the energy go? It comes back as luminescence. And so he said the external luminescent emission ideally is equal to the incoming sunlight, and this is this famous formula that determines the ideal voltage of a solar cell. So we took a few steps from the Boltzmann factor, and we have now derived Shockley's formula for the expected open circuit voltage. Now maybe it was a little bit unsatisfying and a little bit too abstract. Let me show you another way of assigning a voltage to a solar cell. However, for this concept, you have to accept the idea that photons have entropy. Now, you may be uncomfortable with that. Of course, if you're an astrophysicist, they're always talking about the photons having entropy, so it shouldn't be that surprising. But the formula for free energy is often written U minus Ts. So for a photon, U is h nu, and Ts, well, we have to determine what is the entropy. And so the photon free energy, it's h nu, and then the entropy we associate with k log w. So this is like standard statistical mechanics. How many configurations are there for the photon? Is a photon entropy, is that such a hard concept? Actually, it's not so hard. And the reason why it's not so hard is that most of the entropy of the photon has to do with the fact that we don't know the direction that the photon is going. If you're standing outside, the photons are coming from all possible directions. However, it didn't start that way. If you're standing outside, you look at the sun, and those photons started from the direction of the sun. But by the time it scatters through the Earth, through the atmosphere, many of the photons are coming in all different directions. And if we make a solar panel, it has to accept light not just from the sun, but it has to accept light from the other angles. You can't really afford to compromise on this. If in a normal climate, similar to Haifa or similar to San Francisco, 30% of the light is coming from other angles. And so the solar cell is throwing away the angle information. And so the statistical mechanics is talking about the small solid angle subtended by the sun, which is 1/2 degree, versus all possible angles, which is like pi steradians. So it's the ratio of these two solid angles that is the biggest contributor to the entropy of photons. It's rather interesting, but a very simple idea. And it's quite substantial because the sun is so small. This W, the number of possible configurations, the number of places in the sky where the sun could have been, is about 40,000. The sun is so small, there are 40,000 solid angles in the sky, so 40,000 different angles in the sky where the sun could have been. That information that it was in one of those particular angles is thrown away, and so you get entropy associated with that randomness. It's the ratio of these two angles, and it's natural log of 40,000, it's about 12, and immediately it becomes kT log of 40,000, which is 12 kT. You lose almost 0.3 of a volt. This is the biggest entropy of sunlight, surprisingly. Now, there are a few other terms. There's a term associated with this 4n² factor. The way to think about that is that when the light is coming into the semiconductor, it refracts, and the angle is even smaller. And so there's even more information you're throwing away. So you pick up another natural log of 4n², that's another 1/10 of a volt. You have a 1/10 of a volt to give the electrons and holes a reason to go into the wire. And that has to do with the fill factor, so et cetera. There's another loss if you have bad luminescence. And then there's some other small correction terms. So this is kind of a nice way of thinking about the free energy of photons. It's the photon energy minus a bunch of entropy terms. And I'm following here some work done by a student from Berkeley, but it was a long time ago. It was over 40 years ago, but he was a student of Melvin Calvin, and he was actually studying photosynthesis. He was not interested in solar cells. And he worked all this thermodynamics out for photosynthesis, but it's just equally applicable to solar cells. But there are some executive decisions that come out of this. If you add up all of these entropy terms, there's so many and it's so bad. If you add them all up, let's say you start with a band gap of crystalline silicon, all those entropy terms add up to 8/10 of a volt. If I subtract, I get only 3/10 of a volt. So it's very, very important to deal with this entropy problem. And particularly, it's very bad with a low band gap because you're subtracting a fixed amount of free energy. And so if you do nothing, you'll be stuck with a very, very low, just 3/10 of a volt, even though the photons were 2 volts and 2.5 volts. So it's very, very important to deal with this. Okay, so I've summarized now what is the best you can do with current, what is the best you can do with voltage. Now I will describe where the experiments are. There have been some very big changes in the photovoltaic field in the past couple of years. You see it went along, almost 20 years it went along, nothing happened to the record. The record was around 25% efficiency, and then suddenly the record jumped from 25 to 28.8%. So this is rather remarkable to happen. It just happened in the past 3 years. And in fact, the entire new record is not based on current. The current is about the same, but we have new insights to what determines the voltage of a solar cell. So almost all of this record-breaking performance is due to a better understanding of the voltage. The voltage, as I indicated, is subtle. It has to do with statistical mechanics. It tends to be overlooked. And indeed, there is some new physics that is taking us above 25% efficiency. And you say, well, it's somewhat overdue because the theoretical limit was 33.5. We were stuck for a long time at 25. What was wrong? Well, the physics of the solar cell had to be changed. So up until recently, this was the physics of a solar cell. You come in, you produce electrons and holes, you collect the electrons and holes, and that's how you did it. That was how a solar cell worked. We have a new conception of the solar cell now. The new conception is indicated in this slide. And it allows the much higher efficiency. And so in this new conception, the photons come in, they produce an electron-hole pair. Electron-hole pair recombines, gives an infrared photon. Infrared photon is reabsorbed, and sometimes it escapes. But most of the time, it is absorbed, it bounces around, it is reabsorbed, bounces around, reabsorbed, and so forth. And you end up with an infrared photon gas inside the solar cell. In fact, it's very common as you go to high performance that you could have only one sun coming in, but you could have trapped internally inside the solar film, you could have 40 suns of infrared radiation bouncing around. So if you arrive at that condition, this is very desirable. And it means that the really high efficiency solar cells have a tremendous amount of trapped infrared radiation. If you have that, then you go to a much higher efficiency. And this emerged in the past couple of years. Now, what did Shockley say? Well, he said that, look, you have your ideal voltage, and I showed you how he derived it. But if you fail to achieve the ideal, if you have less than perfect luminescence, he said ideally every solar photon coming in goes back as luminescence. That's ideal at open circuit. If you fail to achieve that ideal, you'll have a penalty loss in voltage. This is your penalty. And this is the external luminescence yield. And so if it's very small, which it would be in silicon, because it doesn't luminesce that well, you'll have a certain voltage penalty. And that if you want to achieve the highest voltage, you need to do a really good job extracting luminescent photons. In other words, a great solar cell should also be a great LED. And so from this rather simple formula, we realized that it's actually very, very difficult to get the photons out. For example, they could bounce around internally and then they would not escape. So it's very much like the LED problem. And if you hope to have, let's say, even only 50% external luminescence, then because the escape cone is so narrow, you need maybe 99% internal fluorescence yield. But this is very, very hard to do. 99% internal yield, you know, it's hard. It's achievable in gallium arsenide, but it's very, very hard to do. And if you actually then analyze, well, what is the penalty? You can see by this that the better the rear mirror, this has to do with the rear reflectivity, but it's very similar to the luminescence efficiency. Obviously, the better it is, you do better, but the last little bit gives you the biggest boost. So what it says is 99% efficiency, or 90% efficiency, or 90% reflectivity is not enough. We would, if possible, like to get up here 99%. That would be very nice. And the entire improvement is due to the voltage becoming much, much better as you improve the optical properties. And the current almost is unchanged. This is all about the voltage. And so these concepts were incorporated in the solar cell produced by a company of which I am the co-founder with Professor Harry Atwater from Caltech. And this is an example of the record single-junction solar cell. And the efficiency is actually 28.8%. This is rather remarkable efficiency, but I can tell you how they did this. All they did was to keep improving the mirror. This is not about materials. This is not about transporting electrons and holes. This is about improving the optics. And they went from a 96% mirror, and they broke the record. Then they went to a 97% mirror, and they broke the record again. And a 98% mirror, that's approximately what you have here. So they kept breaking the record just based on improving the optics. And in effect, they went from this situation to this situation. And the more closely they got into this regime, the higher their record was. Both are needed, of course. You need high internal fluorescence yield and high reflectivity. And so to understand then what the issues are in very high performance solar cells, by the time you've reached 25% efficiency, the electrons and holes to transport all the things having to do with the normal semiconductor things you worry about, these are already fine. And any further improvement above 25% efficiency is all about photons. It's all about optics and about photon management. And this is sort of the slogan. The slogan is, a good solar cell has to be a good LED. And here's the part that is very counterintuitive. And is the solar cell performs best when it emits the maximum amount of light. This is very counterintuitive. Why should a solar cell give back any photons at all? It's very strange. And so I will spend a few slides trying to resolve that paradox. By the way, we had a publicity release. The company broke the record. They put out a publicity release. And they couldn't wrap their minds around the idea that the solar cell should be emitting light. And they have all sorts of, it was all wrong. It had all the wrong explanations because it is very hard for us to think that a solar cell performs better by emitting more light. But let me try to resolve that paradox. It's a very strange paradox, but this is the world that we're in. So why is this? Why is it good to emit light? Well, if you're emitting light, that means probably you don't have much non-radiative recombination. And so the good emission is an indication that you don't have non-radiative processes. And so that's good, because anything non-radiative is certainly harmful. So this is one possible explanation. By the way, I have 5 explanations. The reason I have 5 is this is very uneasy to explain. So we're trying to wipe out the non-radiative recombination. That's reason number 1. Let me see if I can go to reason number 2. Well, good luminescence is good. Why? Well, you're going to lose some photons into free space regardless. That's unavoidable. All the other losses at least can be eliminated. So if the only loss is emission of photons, that means you have the least possible loss. And if you have the least loss, then you'll have the highest voltage and the most efficiency. So that's my second explanation. This is suggesting here we want to get the photons out, and we don't want them to become lost internally. So they recombine, they reflect, eventually they escape. Third explanation. This makes some people feel a little better. The photon bounces around, it gets reabsorbed. Well, that means the photon was never really lost. I mean, a recycled photon is not lost. It recreates the electron. If it recreates the electron, the carrier lifetime increases. If the carrier lifetime increases, the density increases. Free energy goes as kT log of density, and so we increase the voltage. This is another explanation. You see, I need all these explanations because this is very uneasy. Okay, fourth explanation. The LED and the solar cell are reciprocal devices. So a good solar cell makes a good LED. So if I have a very good LED and emits well, it will also be a good solar cell. The two are the same device, so they're reciprocal. So it should emit just like a very good LED. Okay, and the last one is my favorite explanation. And this is, I truly believe this, and that is that luminescence is voltage. And in fact, infrared luminescence is sometimes used as a contactless voltmeter. Sometimes in manufacturing, they will take an infrared photograph of the solar panel, and if they see that part of the panel is not glowing infrared, they say, oh, that's bad, that's a bad panel, let's take it out. Okay? And they use this as a diagnostic to know when they have a problem. And indeed, you could see this. Luminescence goes as the NP product. This is a semiconductor formula, and the NP product goes as the voltage. So luminescence is voltage. And it's a tautology. Why do you want good luminescence from a solar cell? Because that means it has good voltage. So that's my preferred explanation. And here it is. It's used as a contactless quality control metric in manufacturing. So this last viewpoint is a tautology. Good luminescence is good voltage and therefore good efficiency. And it all comes from this equation. We're trying to boost the efficiency of luminescence, and that gives us the most ideal open circuit voltage. But people still object to these things, so let me cover a few objections. I noticed nobody interrupted me with a question, so I'll have to introduce the questions, and people have asked. My solar cell does not luminesce at all, therefore why should I pay any attention to you? Okay, and so my answer is, well, you haven't checked closely. If you have a material that does not luminesce well, that's unfortunate. Obviously the voltage is not very high, but there is always a small amount of luminescence. So don't assume that there's nothing there. There's got to be a little something. Okay. Another objection is that people say, well, I need to separate the electron hole as quickly as possible so they don't recombine. And so I don't want to have radiative recombination. And my answer is that this very big electric field, which causes the rapid separation of electron and hole, well, maybe you'll get good current, but it's costing you voltage. And this built-in electric field represents voltage that you will never see in the external circuit. And it's kind of like an internal IR drop. So it's not a good situation to have to pull the electron hole apart very, very quickly. And this third question is a similar question. It says I have to suppress the fluorescence before the electron and hole are separated. And so the suppressed fluorescence, I would say, unfortunately, is an indicator that voltage was sacrificed for current. And it would be good if the carrier extraction was improved. So these are my answers to some of those questions. And if you have other objections, please tell me in the question period. We're almost done. And actually, I was supposed to show you some of these solar cells from Alta. I'll show them to you in just a minute. They're just made of gallium arsenide. They're very thin, about a micron thick. And they lend themselves to dual junction because you can grow this alloy on top. And then you have a very interesting dual junction cell, lattice match, relatively easy to manufacture. And with interesting radiative coupling, the luminescence couples between the big band gap and the small band gap and so forth. So the net result is that you have more performance. And so this is the performance that was just achieved actually 2 weeks ago. They got word from NREL. NREL is the official government agency that certifies efficiency. And in this way, they have now gotten into the next digit. They're up to 30% efficiency now. And so this is something that they're very proud of. And eventually, this type of approach may be close to 34% efficiency. So they're working on it. Now, let me show you what these films are. Well, here's one more slide I want to show. No one questions that gallium arsenide is the best, because where cost is no objection, the gallium arsenide solar cells are used. For example, in space, they don't worry about the cost, and so they are the highest performing solar cell. However, it is possible to reduce the cost. And the way to reduce the cost, this is an old paper I wrote, and you have aluminum arsenide and you bring in acid and you peel the film, and you can peel the film over a big area. Let me show you another slide of peeling the film. This is from Netherlands, but they do something very similar. You have a droplet of acid, it goes in, it undercuts the film, and you peel it. The one up on the screen is only 2 inches. Let me show you the ones that are made by Alta. This is essentially an industrial process now. And they basically have epitaxial gallium arsenide films coming off essentially off of 6-inch wafers and just pulling them off. And it takes a very short time just to pull off a wafer, and then they reuse the substrate. In this way, the cost goes away. And so I'll show you these afterward. Here's one that has been assembled into a small panel. And you see it's just wavy, flappy. You wouldn't think this is a single crystal, but when it's very, very thin, it's very flexible, surprisingly so. But this idea of peeling crystalline films, I've always liked the idea. It's now being adopted in silicon, and so this is called spalling. This is from IBM, who's not a small company, where they're actually peeling the silicon. And so this is an idea. It extends beyond gallium arsenide. They crack the silicon film, and it comes off surprisingly uniform, about 30, 40 microns thick, which is a good thickness for silicon. Similar work from a startup company in Texas, where they peel the silicon wafer. So I have my flexible gallium arsenide, but they have their flexible silicon foils, and they call it exfoliation. And it all means the same thing. And yeah, there's another company here. They are using Smart Cut, which is sort of an ion implantation. They can peel the films. And everybody's always amazed at how flexible single crystals can be. And this is for gallium arsenide. OK, so let me summarize. I see I've used up a lot of my time here. Just to give you an idea of what's going on in the industry, the different technologies have different performance. And I won't dwell on it. Instead, what I'll tell you is what's really going on in the industry is there are tremendous subsidies in China, and everybody is losing money. And so although silicon is up at 90% market share, the cost of the panels is now dropped well below $1 a watt. People say as low as 40 cents a watt. This was supposed to happen 10 years from now as a result of technical improvements. Instead, it's happening right now, not for any scientific reason, simply a price war. And the Chinese are losing money, and all the other companies are losing money. On the other hand, this is saving Germany a huge amount of money, because now they don't have to have an installation subsidy because China has a production subsidy. So it's quite interesting. But there are other contenders. There's this copper indium gallium diselenide. There are maybe 100 startup companies on this, but the efficiency is not that great. There's CAD telluride. I showed you CAD telluride. There's one major company in CAD telluride, but the efficiency is not that great. Flat plate gallium arsenide, I showed you. Well, I guess this is out of date now. A dual junction is now 30%, which is pretty good. Triple junction concentrator, it looks higher. Actually, I think they've now reached 44%. However, you have to be very careful when you evaluate concentrators. They're using only 70% of the sunlight. And so the efficiency should be multiplied by 0.7. And in that case, it looks similar to the flat plate technologies. So these are some of the top technologies, but crystalline silicon is still completely dominant. I don't think it's for a scientific reason, it's just the way history has evolved. The subsidies have poured into the technology that was most ready, and huge subsidies have poured into silicon production. So they've managed to get their costs down. So I think the future is that we are looking at very low-cost panels. The costs that were supposed to be achieved far in the future are already here, and we need to think about other applications other than maybe producing electricity, maybe producing fuels. I think the future is still wide open. There's still further cost reductions to come. Okay, thank you for listening.
Any question for Eli?
Return please to the slide where you show the random reflections from the rough surface.
You're right. How about this one?
Yeah,
go ahead.
So you have the beam going in various directions.
Yeah.
And you're interacting with a crystalline semiconductor which has a dipole moment orientation. So with approximately, I would assume, half of the directions you would not be able to interact. What about considerations of the orientation of the dipole moment?
Okay, so the question, it's kind of a subtle question. It has to do with the fact that optical absorbing materials have a dipole matrix element, and it's a vector, and it's pointing in a certain direction. This is certainly true of all semiconductors. But keep in mind, these are not nanostructures necessarily. These are actually bulk materials. The example I showed at the end could be 30, 40 microns thick. And when we talk about the absorption of silicon, the optical absorption of silicon, we have already taken into account that some of the dipoles in the bulk material are pointing in an unfavorable direction. And so the known absorption coefficient of the indirect edge is already taking into account the very important effect that you're invoking. So it's something we have to live with. Okay.
Or you can try to use some polysilicon which has different dipole.
Well, I think in the spirit of nanophotonics, we would maybe use some kind of quantum dot where there's one of the wave functions is oriented in a particularly favorable direction. We're not in that regime at this time. At this time, we're using materials that are maybe a little bit thicker. If we had a quantum well, we'd have to worry about this quite a bit.
Thank you. Going back to your last slide, I noticed that amorphous silicon is not in the list. So can you comment on that?
Well, you know, it's just my personal opinion, and so I'm sure there are people who disagree with me, and I'm surprised that you have not attacked me on this before. So it's sort of an executive decision what I think is happening out there at the commercial scale. The amorphous silicon had difficulty breaking through 10% efficiency. So it's been really superseded by the cadmium telluride. And it's just one of those historical things. It looked good for a certain period of time, and now other things are now the champions of low efficiency solar cells. So right now, if you can tolerate low efficiency, cadmium telluride seems to be the dominant material. It is also the one that is dominant on Wall Street. That company is the most highly respected.
Thank you.
More questions?
I understand that band gap is translated into voltages, therefore a higher band gap will be more desirable material. On the other hand, you lose at some point you lose absorption. So what do you suggest about optimization of the band gap of the actual material?
Well, that's a very good point. And so this question is about the band gap optimization. I think we have to take very seriously the fact that we really don't want a small band gap because we're subtracting a fixed amount of the entropy term. It's a TS or KT log W. This is a fixed subtraction from the band gap. And so what it suggests is the infrared band gaps are not very desirable because you end up subtracting almost everything. And I am trying to emphasize to people that please don't spend so much attention on the infrared photons. They may carry a lot of energy, but they don't carry very much free energy. I'm strongly recommending instead concentrate on the blue photons. The blue photons are capable of very big voltages, and yet that voltage is wasted now. And that's where I think a lot of the free energy remains. However, if you try to optimize a single band gap, this was already done by Shockley, and it worked out to be around somewhere between 1.1 and 1.4 volts band gap. That's a single band gap optimization. Then you have dual band gap optimization and so forth. But the most important thing in my view is to have a solar cell that does a very good job with the bigger photons. If we had a photovoltaic material with a 2.2 volt band gap and a 1.8 volt open circuit voltage, this would be quite fantastic. That would open up the full efficiency potential of dual junction and bigger junctions. So I think the future is very much lying with splitting the solar spectrum and getting really big voltages from the really big photons.
So gallium nitride for? So nitrides for solar cells as well?
Yeah, there is some research on the nitrides. They're a little too big for the solar spectrum.
You can tune it.
You can tune it. If you can show me a good 2.2 volt band gap nitride, I would have a lot of uses for it.
I have a question, a very naive one, probably related to the statistical mechanics description. You have another alternative, which is just absorbing photons in some medium, getting the temperature higher and build a heat engine out of that. That would probably give you very low efficiency because the temperature increase is somehow limited. So if you think about those devices in terms of heat engines, since they have higher efficiency, then there should be some higher effective temperature.
Right.
And what is this temperature? Is it the photon bath temperature or the electron hole?
So the question is, how well can you do with a heat engine? A lot of solar research is dedicated toward thermal heat engines. And typically, I know this is in the negative, they have done this type of research where it's a concentrator. So you concentrate from a big field onto a big stationary heat sink, which often has liquid sodium in it. And you try to make it as hot as possible. You go hundreds of degrees. And it's a thermal engine. It has certain advantages because it stores the heat overnight. And so you get electricity at nighttime. So that's inherently valuable. On the other hand, it doesn't lend itself to cost reduction because it's basically a big, complicated steam engine, and it needs tracking. It's constant. It has all the disadvantages of concentrators. So a lot of demonstrations have been built, yet you don't see the kind of cost reduction that we've seen in the usual semiconductor approach. So as far as efficiency is concerned, it's also maybe like most heat engines in the 30% efficiency range. That's not bad, but you're throwing away a lot of the diffuse light. So there are some limitations there. So a lot of effort has been, and money has been spent. So it's a matter of opinion. Is that the right way to go? Or is it better to go with flat panels? The flat panels work on houses, they work on small installations, they also work on big installations. Their costs are coming down very rapidly. So it's obviously room for many different opinions.